everything with you, so you don't have to keep looking for it, like keep searching for it. So make sure you have all your formulas that you need. And pretty much, I think once we got into section 1.5 is where we started looking at some kind of formulas going forward. I think up until we did 1.1 through 1.4, you were mainly using the right triangle trigonometry, the unit circle, and stuff like that.
Oh, yeah. Yeah.
So, because remember, we had talked about the 30, 60, 90 degree triangle. We had talked about the 45-degree triangle and stuff like that. But once we got into 1.5, I believe, is where we started looking at, we talked about those different identities, the trig identities. We, of course, had your formula, for calculating the period and stuff like that. When we got towards the end of chapter 8, we looked into those harmonic motion types of equations.
Mm-hmm.
So just kind of make sure you're able to work through those different types of problems. Because, there are going to be questions from each section pretty much, just to make sure you are comfortable with each concept that we looked at each of the different sections. And then I think it was, I'm trying to find my page here. Yeah, it was section 2.1 where we brought in all those Pythagorean identities. Of course, we talked about the quotient and the reciprocal identities, and then how to see if our functions are odd and even. We also had co-function identities. So, stuff like that. And you should have these in your handouts as well, but just make sure you're kind of keeping all these identities and these rules handy. So, if you come across a question, you don't have to go searching for them. Because since your final exam is going to be timed and you're only getting one attempt on the final exam, I just want to make sure you won't run out of time or anything like that.
Mm-hmm. Is it like a class period?
Yeah, so I'm actually giving you guys an hour and a half, and then I'm going to tag on a couple extra minutes just to give you time to get started, get your exam started, get all your stuff together. But yeah, I mean, it's about hour and a half. And if you need a couple extra minutes, you should be okay with that.
Okay.
And then remember, towards the end of chapter 2, we started talking about those sum and difference formulas. We had the product to sum to product formulas and stuff like that. I think 2.4 and 2.5 is where we had a majority of those formulas show up. And chapter 2 was also where we talked about how to verify those identities, how to solve equations involving trigonometric functions. So that would be something I would definitely ask you guys to kind of review over. And then, yeah, it's showing 2.4 is where we did the sum and difference formulas. Section 2.5 was where we did the double angle formula, the half angle formulas, power reducing, and then, as I was mentioning, the sum to product and the product to sum. So obviously I'm not going to be putting like too many questions from those sections, but you will definitely see a couple examples from each one of those, or a couple problems from each one of those sections. So those would be the ones I would definitely work towards. Then in chapter 3, we looked at law of sines and law of cosines. So remember, it depends on what information is given to you in your triangle. And these are, of course, remember the oblique triangles where your angles are not 90 degrees. So you kind of have to see, are you given two angles on one side? Are you given two sides and an angle opposite? All three sides are given to you, or, two sides with the included angle. Because based on that, you would need to decide, are you going to be using law of sines or law of cosines? And then in these two sections, we also looked at two different formulas for calculating the area of our triangle. So just make sure you have those formulas with you also, because again, depending on what information is given to you, you will need to use the area formula based on that. Also to keep in mind that you will have a few application problems in there also. So just, again, kind of see what information is given to you, and again, which technique from which section you would need to kind of bring in. From that, then, kind of we did the part of chapter 4 where we talked about the complex numbers and the complex plane. So you should expect to see 4.1 was more of a review section, so I don't think I have anything in the final for 4.1, because if you do anything in section 4.3 or 4.4, you are using techniques from 4.1. So I would concentrate on just, again, the different things we talked about in 4.3 and 4.4. So 4.3 was where we brought in the complex plane, and we talked about how to graph our points in the complex plane. We talked about the distance formula, the midpoint formula, and of just your basic adding, subtracting, multiplying with complex conjugates, and that kind of thing. So section 4.4 is where we're looking at the trigonometric form for a complex number. So that could be a conversion type of example you could come across from 4.4. And then, of course, in 4.4 also, we talked about how we can multiply and divide complex numbers. I can't remember if we had done any application in those sections. I don't think so. Because I think applications were mainly in chapter 1, chapter 2, chapter 3. Then I think after chapter 4, we went directly to 6, which was the last two sections we talked about, 6, 7, and 6, 8. So this is where, we're all talking about polar coordinates. Now, we actually introduced polar coordinates. I'm trying to remember. I think this was 1.5 or 1.6 or somewhere. We kind of briefly introduced them. We just didn't really identify them as polar coordinates. So just kind of be a little careful about how you can graph polar coordinates. And of course, as you've seen in your homework, that graphing is going to be mainly about choosing the right graph. And then this is where we talked about conversions in 6.7, where you are converting them from the rectangular form to the polar form, or vice versa. So you can have ordered pairs that need to be converted from the polar to the rectangular form, or backward. You can have equations that need to be converted from the polar form to the rectangular form. So those were the main things that we looked at in section 6.7. So again, just being comfortable going back and forth between the two modes. And of course, your last one, section 6.8, was all about graphing these polar equations. So remember, this is where we had those Limacons and the lemniscates and the rose curves and all of that. So this one would be mainly about identifying your graph, and maybe a question on finding the symmetry for your function. What kind of symmetry does it have with respect to the pole, or the polar axis, or the vertical line, theta equals pi halves. So something of that sort. So definitely expect to see a couple questions from each section of 6.8 and 6.7, since that's the last thing we talked about. And then you should kind of expect evenly distributed questions from the remaining sections. And again, guys, I cannot insist enough that make sure you have all your formulas handy and everything ready to go, because you don't want to lose time in trying to find which formula to use for what kind of problem. And of course, your exams will be timed and they will be password protected. So just make sure you send me that email to get your passwords. You will have all day today and all day tomorrow till midnight tomorrow to take your final exam. And then once you guys are done taking your final exam, then I'll go ahead and calculate your overall grade. And out of the chapter exams that you have taken, I will be dropping the lowest chapter exam score. So that should kind of help you, just get rid of that lowest score and keep all the higher ones that you have. So hopefully that will also help, bring up your overall grade. But as far as review goes, did you guys have any specific questions you would like us to go over?
Not really. I think the book gives us formulas for. Yeah. Inside our book, it gives us the formulas for all on one page. As a formula page.
Oh,
Yeah.
does it?
Yeah, it's like at the very end.
Okay.
It's got definitions of the 6 trig functions, and then it just has all of the formulas.
Okay, so as long as, they have everything that you would need.
Mm-hmm. Everything I need right here.
You should be okay then. Oh, okay, on the back page, the very last before the cover, I think.
Mm-hmm.
Okay. Huh.
That's a pretty useful page.
Yeah, I see the circular functions, the triangle or reciprocal identities quotient. Okay, they do have quite a few of those. And they have a unit circle. Okay, so that's really good.
Yeah.
Yeah, I mean, and obviously we definitely are considering these as open book, open notes kind of exams. So yeah, like I said, just have all of this ready when you get started with your test. It looks like they don't have your law of sines and law of cosines on that page. So I would just, like I said, you can, I don't know, I guess law of sines and law of cosines, you don't have the paper handout since we were already away from school at that point.
So just bookmark that page.
Yeah, just bookmark that page or something like that. So you should have all the handouts right through chapter 2, but then after that, yeah, you would not have the paper handouts for those. And then, yeah, just the formulas and stuff you would need for your chapter 6, converting from rectangular to polar or polar to rectangular. Those might be something you want to keep handy. Complex plane, converting from complex plane to trigonometric form. I think you guys should be okay with that. But again, if you need to keep those kind of things just visible, you can do that also. But yeah, definitely law of sines and law of cosines would be something nice to keep handy with you.
Yeah.
But looks like for most of chapter 1 and chapter 2, you have everything on that one last page.
Yeah.
Okay. And are you guys feeling okay in terms of just
rectangular.
solving any kind of problems, any types of examples?
Yeah, I'm okay doing that.
Okay. So, even if you don't get a chance, because, the practice final is not for a grade, I would just at least skim over those questions just to make sure okay, when I look at a question, this is a strategy I need to solve this. At least just by looking at the question, you would know, okay, this is what I would go about using to solve this. So that way you at least have an idea of what the technique is for solving each question. I would, like I said, there are going to be a few application problems in your final. So just kind of look through the different applications we've done in class or in homework, and just kind of make sure, again, you're comfortable with what the application is asking you to do and how you would go about solving it.
Okay.
Anything else coming to mind, guys?
We were thinking about taking our exam after like today's Zoom. Do you think you could just like send us our one-time password after the meeting?
Okay, so are you thinking of taking it today itself?
Yeah.
Okay, I can do that, not a problem.
Okay, cool. Could we go over some 2.1 problems?
Okay.
And using identities and identifying identities and verifying identities.
Okay, let's take a look here.
things of that nature.
And then these ones, unfortunately, remember these problems given to you in your homework is kind of like those fill in the blank type of problems.
Oh, yeah.
That's the one drawback of this program. I wish they would have just left it open. But yeah, let's take a look at 2.1 over here. It doesn't look like they have a whole bunch on the verifying part, but let's look at something like number 9 over here. So this one is saying use the fundamental identities to simplify the expression. So where can we start with this guy?
We could probably start off by turning secant into 1 over cosine squared.
Okay. So if you're leaving that sine square as it is, and you're turning secant into 1 over cosine squared.
Mm-hmm.
Okay. All right, now what?
We could use, yeah, like a dead end. Yeah. Wait, quick.
Is basically
Sine.
if you have sine over cosine.
Yeah, that's what I was gonna say. Heck yeah. So that just turns into tangent minus sine squared.
Okay.
Okay, now that we have minus sine squared, could we?
Because what I was actually thinking, instead of going down this path, what if you had taken the sine square outside as your common factor?
Oh.
Right? And then you would be left with secant squared of x minus 1. And do we have an identity that would help us out with that?
Secant squared minus 1. Oh. Where is it? Tangent squared? Yeah, tangent squared plus 1, or 1 plus tangent squared. Well, the 1 minus.
No, because you're taking the minus to the other side, right? So shouldn't this guy just become tangent squared?
Yeah.
So then you would end up with sine squared x multiplied with tangent squared x. So I think that would be a better answer, though this one technically is not wrong. But for the most part, we were kind of getting our answers to look more like this. But, you know, I am not sure what the programming information in these guys is. So I'm not sure what answer they would accept. I think on paper, we would have probably accepted both of them.
It does say that there is more than one correct form of the answer.
So yeah, that's what I don't know, like what their programming would be like, because, you know, computer programs try to kind of do what they want to do.
Yeah, that's true.
But does this kind of at least make sense how you would go about solving it by looking at both methods?
Yeah. Yeah.
Okay. So just just to show you the separation between those answers. How about something like number 12 over here?
Sine plus 7. How did you get sin squared? It is 1 minus cosine. I mean, negative 1 plus. Oh, yeah.
So where did you start on this problem?
I started out by defining sine squared as using the the Pythagorean identity
Okay, so
of
what did you
sine
write
squared.
there?
So I defined it as cosine minus 1. I mean cosine squared minus 1 plus 7
So it should
cosine.
actually be the other way around because your Pythagorean identity is sine squared plus cosine squared equals 1. So when you substitute for your sine squared, it should actually become 1 minus.
Okay. Oh, okay. So then that becomes 8 at the end. Yeah. Times what? Yeah, 14.
You know, if factoring becomes easy, you can take that -1 as an outside common factor and change the signs on everything.
Because 2 times 4 is 8. Added together is 9. That's 6. What? Oh, it is, yes. Whoops. That. You could use the trigonometry. Or you can always use the quadratic formula. Yeah. I think we might have to because 7 is prime. I'm multiplying 2 7. That's shit. 89. Necessary factors.
So what two numbers multiply to give you -8 and add up to give you -7?
-1 and -8, or no, -8 and 1.
Yeah, -8, +1. So these guys will factor into cosine of x. What was that? +1 and cosine of x -8.
Yeah.
Yeah, because that would give us -8 and -7. Yeah, so you can basically just have negative of cosine of x +1, and then the other factor would be cosine of x -8, and there you go.
Voila. Equal to 0.
Well, actually, these guys are not equations, so you don't have to set it equal to 0. So did you guys come up with this?
Yeah.
Okay, very good. Do you have any questions about it?
Nope.
What will you guys do for number 13 over here?
Secant minus cosine. Let me see. Would I turn the secant into 1 over cosine?
Okay. So cosine of x on the outside, 1 over cosine of x minus cosine of x, okay?
And then could I distribute the cosine of x? That way it's just cosine of x over x minus cosine of x, or squared.
Yeah.
And that gives you a trig identity.
You end up with cosine of x over cosine of x and cosine squared of x here. Okay, and then what will that clean up into?
1 minus cosine of x squared, or cosine squared x.
Yeah, very good. And
that just comes out to one of the trig identities being sine of x squared.
yeah, because this is coming from that Pythagorean identity, so this will become sine squared x. Very good.
I did it.
Alrighty, good job. Okay. For anything like 15 or 16, what would your strategy be?
Multiply the denominators, like cross multiply, basically.
Yeah, so kind of like finding common denominator, right? So this one, of course, that means this whole fraction would need to be multiplied by top and bottom by 1 plus cosine of x. This one would, of course, be multiplied by 1 minus cosine of x. Same thing here. Top and bottom, you would multiply by 1 plus cosine of x. This would be multiplied by sine of x. And then you would need to clean it up based on that.
Yeah.
Right. Okay. Now, I actually did want to look at these kind of examples over here. So like maybe like something like number 18. So they're asking us to use the trig substitution to write the algebraic expression as the trigonometric function of theta, and your theta is between 0 and pi half. So what would we do here? So when they're saying use the trig substitution, what do we do?
We're gonna substitute the x for the trigonometric function.
Okay, so what will you end up getting?
64 minus 8 sine theta all under the square root.
Okay, and what happens with the 8 sine theta? Because you've got x squared here, right?
Yeah.
So shouldn't this guy be a square also?
Mm-hmm.
Yeah. So when you
Does it turn to 64? And then the sine becomes sine squared theta?
yeah, very good. So yeah, you will get 8 squared, which is 64, and that will make it sine squared theta. And then what happens?
Do we factor the 64?
Uh-huh. So that will leave us with
Is it negative sine squared of theta?
you should have 1, right? Because you have a placeholder for this 64. So you should have a 1 for that, and then minus
Oh,
sine
okay.
squared theta.
Then that's just cosine squared.
Very good, yeah. And now when you clean this up, take the square root, what will you get?
8 of cosine.
There you go. Yeah, that's the entire process. Very good.
Yeah. Okay.
Does that make sense?
Yeah.
Yeah, okay, very good. And I think these are just variations on
That
that.
problem.
Are you guys okay with something like number 14 here?
Yeah. Let's go over it.
Okay. So what do we do here?
Isn't it you just multiply together, so it's just going to be 4 cosine or cosecant of x minus 4.
Yeah, so you either do FOIL, or you can, since these are, remember these are what we call as conjugates. So since you're multiplying conjugates, you're just taking the square of the first term minus the square of the second term. So 2 cosecant x multiplied with 2 cosecant x will of course give you 4 cosecant squared x, right?
Yeah.
And then the 2 times 2, of course, will give you 4. And then how would we go about simplifying this?
Could we pull the 4, so it's 4 cosecant squared of x minus 1?
There you go, very good. And then?
And then it's 4 secant, 4 secant squared, right? Is that a trig identity?
You would have to use the trig identity. So what does the identity, which one are you using here to make the substitution?
Would be the pet, no.
It will, yeah.
Oh, okay. Diagram identity?
Uh-huh, so what will we substitute this parentheses with?
Cotangent?
Okay, and what will it be? Just cotangent?
Cotangent squared.
Squared, yeah, of x. Yeah, and of course, this one you don't have square root or anything, so you don't have to worry about reducing this down, but That's how far you'll be able to go.
Cool.
Okay, let me see. What else am I seeing over here? Okay, look at those guys. These are just different forms of factoring. Let's look at number 10 over here. Where would we need to even begin with this guy?
Would we turn tangent into secant? Or try to turn it into secant?
We can try. So what
So,
relationship would
or
you?
let's also take secant and turn it into cotangent, so that way it's just all cosine and sine.
Okay, so you said take secant and turn into cotangent?
Or the cosine, sorry. Into the
Cosine?
cosine line. Yeah.
Okay. So
So
what
that way
would
it's
you?
1 over secant, or 1 over cosine squared. Or not squared.
Fourth power, right?
Yeah.
Okay, so secant you're rewriting as 1 over cosine to the fourth power. Okay, and then what are you doing with the tangent?
The sine of x
And again,
over
fourth
cosine of
power.
x to the fourth power.
Okay, alrighty. That's a good
And
start.
then they already have the same denominator, so you could do 1 minus cosine to the fourth, or 1 minus sine to the fourth power over cosine to the fourth power.
Okay, there we go.
And then 1 minus sine to the fourth power, is that just cosine to the fourth power again? Would that be what that is?
That's
So
what
1
I was
minus,
kind of thinking, because I'm not sure.
you could probably break up, so it'd be like 1 minus sine squared and then 1 plus sine squared.
Yeah, that's what I'm kind of thinking. You may have to use factoring, because I'm not sure just by raising each one of these to the second power is that going to work? Okay, so if you used factoring here, you would have, because you're basically, you have a square minus b square, you're factoring it into a plus b, a minus b, so that would be 1 plus sine squared of x and 1 minus sine squared of x over your cosine to the fourth power of x. And what will happen with 1 minus sine squared of x?
It'll turn into cosine x squared, and then that'll cancel out on the cosine of to the fourth power.
Yeah, exactly. Very good. That will become cosine squared of x, and then reduce down with these, leaving us behind with 2 of these.
So it's just 1 plus sine squared of x over cosine squared of x.
And I'm trying to think if we can leave it like that, or do you think we can simplify it further from there? Because there is actually one thing we could do, I think, to simplify these. Could we not?
Probably transform the cosine into 1 negative. No.
I was actually thinking more in terms of what if we took a negative sign outside, and that means no, but we would be making the 1 also a negative.
Yeah.
Because I was trying to see if we could make 1 a negative, leave sign a positive. I'm not seeing that. Okay, so can we not simplify it anymore from here?
I don't think so. Maybe we could, no, because that would just making it more busy.
Yeah, because I was kind of thinking if we had that initial term of secant to the fourth and tangent to the fourth, that would again factor into secant squared of x minus tangent squared of x and secant squared of x plus tangent squared of x. And then secant minus tangent ends up becoming 1 using our Pythagorean identity again. But then you are still left with 1 over secant, which would still be 1 over cosine. This would still be sine over cosine in squares. And we're still getting the same answer, right? 1 plus sine squared x over cosine squared of x. I think, yeah, this is probably how far we go then. It just feels weird leaving our answer as a fraction because most of the time we try not to leave them as fractions.
Mm-hmm.
But I am not seeing how else we can convert it to get rid of our fractions. Because 1 plus sine needs to be 1 minus sine if we're going to make that substitution. I guess this is it, guys. Yeah.
Wow.
So, yeah, so just to show you again the way, I think Ezra, you came up with this, right? Of writing it as 1 over cosine and sine over cosine.
Yeah.
So if you just use that method, or I actually use this factoring process, and looks like we're still coming up with the same result. Okay, not a problem. Okay, so let's move that. Oops. Then we talked about these. These are just samples. Okay, what else did you want to look at?
Wait. I think that was like really it. Just getting to them. Now it gives me, I'm pretty comfortable with the law of sine and law of cosine now. No, yeah, that was pretty much all that I was worried about.
Oh, okay, okay.
Maybe we could try an example from like 4.3.
4.3, okay.
The complex plane and subtracting and adding, but I think I'm pretty comfortable with that as well, maybe.
Okay, not what I was hoping to open. 4.3. There we go. Okay. So did you say adding, subtracting, or what specifically in 4.3?
Not really adding and subtracting, I guess. More specifically, the distance formula. That's what I always struggled with.
Oh, okay.
Just a little sub-bit. The distance is what I've been having problems with.
Okay. Okay, so let's do a quick example on the adding, subtracting, and then we'll move to the distance formula here. So let's look at number 11. So what do we do when we are trying to add these numbers?
You take the real numbers and the imaginary numbers and you just add them together. So 9 minus 1 is 8, and negative I plus 4i is 3i.
Positive 3i, yeah. So yeah, you do, like you said, the real part with the real part and the imaginary with the imaginary. Okay, very good.
Cool.
Now, the only thing you have to be careful about when you are doing subtraction, like here in number 13, what would we need to pay attention to?
The negative sign in front of the 2, or inside it, in front of the parenthesis.
Yeah, so you need to remember to distribute that negative sign. So that would end up giving us negative 2 plus I stays the same, but then the second part would now become negative 2 and minus I. And when we combine these, what do we get?
Just negative 4.
Negative 4, yeah, because these two guys you add up together and then positive I, negative I cancel each other out. very good. Now let's look at the distance formula. Okay, let's do number 16.
Distance formula is s minus a. So -4 minus a -9. And these are squared.
Yeah.
And then 1 minus, or 9 minus 1. Yeah. These are also squared. So 4. 4 squared, 16 minus 81 squared.
Just be careful because you're going to have a whole bunch of negative signs here.
Why is that minus 81? They screwed it.
So for the s minus a squared part, what are you getting?
I got -65.
Negative.
Or wait. No. It should be negative. Is it just positive 65?
Okay,
No.
so let me see. I'm
I need
talking
to.
about this part here. Is that what you're telling me? Or are you telling me for the whole thing?
For the whole thing, sorry. Or no, I'm not telling you for the whole thing. I'm telling you for that part.
Okay, because you know what's happening here is, let's get rid of this for now. What's happening here is when they say s minus a, yeah, s minus a, you're taking this number and subtracting it from this one, right? So you've already got negative on the 4, then you are subtracting -9 from that. So you should have 2 negative signs in here, which will end up becoming positive. So you're basically looking at -4 plus 9.
So 5?
Yeah, so that would be 5 squared. And then for the second part, for the t minus b, what do you get?
8.
Right, so that would be 8 squared. And then when we do 5 squared, that gives you 25. And what's 8 squared?
64.
Very good. So what does that come out to be?
81? 89.
89. Very good. And can we simplify square root of 89?
No. No.
Is
Oh, we can.
what
Let me just figure it out. 89. Oh no, it's just square root of 89. We can't simplify it any further.
Yeah, because I don't think, I don't remember, but 89, I have a feeling might be a prime number. So you may not be able to break this down anymore. But yeah, there you go. So you will end up getting square root of 89 as your distance.
Cool, let's try the next one.
Yeah, sure. Let's go ahead and clear this guy out. All right, let's look at 17.
And 6 plus 4 is 10.
Okay, be careful there because you are doing, well, yeah, the 2 negatives will become positive, will they not? Because you are doing 4 minus -3 on the first part and 6 minus -4. Yeah, so you should be okay.
Cool. So then 4 plus 3 is 7.
Very good.
7 squared is 49. And then 6 plus 4 is 10.
Very good.
And 10 squared is 100. So it's
Alright.
149. And that's your answer because you can't simplify any further.
You can't simplify any further, okay. Since that would add up to 14 or a 5, so it wouldn't go into 3 either. Okay, looks like we can't break this down. So again, that would be your distance.
Cool.
Are you guys okay with the midpoint?
Yeah, I'm pretty good with the midpoint. Yeah, same here.
Yeah, because this is pretty much the same thing. Only difference is you take your real numbers and you add them together, divide by 2, right? So negative 7 plus 1 divided by 2 will end up giving us what's
Negative
that?
3.
Negative 6 divided by 2, so negative 3. And then for the imaginary part, you are again just only interested in the number, so you would take the 4 and add that with the negative 2.
It's just negative 1. Or no, it's just 1.
Yeah, because you're basically doing 4 added to a negative 2 or 4 minus 2. The 2 over 2 would end up giving you 1. Yeah. So midpoint is not that bad as long as, again, you know, for most of these, you just want to make sure you're keeping track of all those signs you have in there. So same thing for the distance formula. Just be careful about the signs that the numbers themselves bring. And as long as you follow that, I think you should be okay.
Cool.
Okay. All right. What else did you want to look at?
Chapter 5. 6, I'm pretty good on. Chapter 3, no, chapter 3 is fine. No, I'm pretty good with everything else that we've covered in the units.
Okay.
Same here.
Adrian, are you saying same also? You're okay?
Yeah, I'm good.
Okay. Okay. And you guys are okay on chapter 6? Were you able to get all that assignment completed?
Yeah, we got that all done. Yeah.
Okay, so no questions on that one either?
Nope.
Okay. Well, I mean, if you guys have no other questions, then that's all I had planned. But, you know, feel free to send me an email between now and whenever you start taking the exam. If you feel like there might be something you want to just maybe go over once before you take the exam, we can do that also.
Okay.
Okay. So I'll go ahead and send you your passwords and let me know if you have any questions before you get started. So just keep in mind, guys, only one attempt. This will be timed, so just make sure that when you sit down to take your exam, you are dedicating that whole hour and a half, hour, 40 minutes, whatever you need to the exam itself, so you don't run out of time, because that's really the main thing I'm worried about. Okay? Alrighty, guys. Well, I just wanted to say thank you. I really appreciate you for sticking, you know, with the class till the end, and I wish you all the best for your final exam, for the other exams you will be working on, and I hope you have a wonderful summer, and hopefully I'll get to see you guys again in the fall semester, either on campus, or I don't know if you end up taking another class with me.
Yeah, hopefully.
So, yeah, I wish you all the best. So have a wonderful time, guys, and good luck for today.
Alrighty.
Right,
Bye.
thank you so much.
Have a good summer.
Bye. Thank you. Bye-bye.
Thanks.